examples, give you some fundamentals on surface preparation and the way that we can make sure we achieve the best bond possible, give you some information on some of the key adhesive types with regard to structural assembly, talk about one or two product highlights, and then focus on 2 or 3 case studies which demonstrate how customers have utilized and implemented adhesives to their benefit, a couple of key takeaways, and an opportunity at the end of the seminar to ask some questions. Before we begin, I just want to give you a very brief overview of some of the markets. I mean, because structural bonding can be implemented in any general manufacturing industry, we're found all over the place. We sometimes focus on more industrial markets like wind turbine, agriculture, and so on. And we have a division that look after electronics and handheld displays. So if any of you are mobile phone users, Apple, for example, they are a major user of Henkel adhesives. So on the question of markets, there's a question in front of you now. If you could respond to this, just so that we get an idea of which market that you're in. Okay, so the result of that is that 2/3 of you are in, excuse me, in the general manufacturing industry, and 1/3 of you are in the electronics industry, which is good news because it means that we're talking to an audience that will have opportunities for adhesive bonding. So that's excellent. Thank you. It's quite difficult to define what a structural adhesive actually is, because one could argue that if you're using an adhesive to bond any parts together, then it's part of the end assembly. But we like to think of structural adhesives as being high performance, high strength, having really long-term durability and adding permanently to the structure. So, for example, the motorhome that you see at the bottom of the picture, we're talking here about the assembly of the side walls of this vehicle. We're talking about joining the structure together, the chassis to the side walls, the roof to the side walls, and so on, rather than perhaps smaller plastic trim parts, which we wouldn't necessarily include in high performance bonding. And we tend to consider structural bonding in 2 ways: either rigid structural bonding, which we would consider with epoxies, polyurethanes and acrylics, or flexible bonding, which we would think about with silane modified polymers or silicones. Now, just to give you an idea of the difference, here we have a structural epoxy, which you can see is quite stiff and certainly not stretchy in any way, whereas from a flexible bonding position or point of view, we've got a silicone or a modified silane, and you can see here very, very stretchy, completely different polymer that's been formed. And we'll talk about the differences and where they would be used and why they would be used as we go through the presentation. Inevitably, we have to consider conventional joining methods as our competitors. And why would we move away from conventional methods and move on to structural bonding and adhesive bonding? Well, because we use the entire bond area within a bonded joint, we have lower peaks of stress, and therefore we can take higher loads across these areas that are joined. And the other advantage with adhesive bonding, of course, is that we're not doing any damage to the materials that we're joining. So we can take 2 pieces of aluminium or steel or any combination of these metals. We don't do any metallurgical damage to them during the joining process. We don't weaken them by drilling holes. we don't weaken them by welding, if indeed welding is an option. And of course, the other advantage is that we can take aluminium and we can, for example, and we can combine that with any other composite material and still use adhesives, whereas traditional joining methods would become very difficult. We also have the advantage of bonding and sealing the joint at the same time. There's probably no better example of this improved stress distribution than this one here, which on the left-hand side shows you a riveted box beam, so two top hat stiffeners joined together. And on the right, we have the same geometry, but the flanges are entirely bonded. Now, the next series of pictures as I go through, what you'll see is from the left-hand side, there is a significant, there's a high-pressure ram and a high-speed ram that will be impacting these as we go through. So as I start to bring these pictures through, you'll see that the first thing that happens with the riveted beam is that there is a fold occurs right in the middle. So this initial impact, irrespective of where the mechanical fasteners have been placed, there's an immediate fold in the middle of this beam. And as I run through this, again, you can see that fold taking place. And in the next picture, you can just start to see the rivets of the part of the beam that as yet haven't been touched are still coming free and loosening. Here you can see the rivets at the bottom of that beam. And as the ram continues, so the beam is just continuously destroyed, and actually the ram or the bar at the bottom of the picture, which is the stop point, also takes a bit of a clatter as the test goes through to completion. If we compare that now to the bonded beam on the right hand side as we go through, the first thing to notice is under that first impact, we don't have this horrible and immediate deformation of the entire structure. And that's because all of these flanges are contributing, because we have adhesive on the whole flange area, all of that is contributing to the resistance of this impact test. And if I run the same sequence through, here you can see that we get a nice uniform folding of this beam, not this catastrophic bending and catastrophic failure. I'll run it through a couple more pictures. We continue to get this controlled folding. And if I take it through to completion of test, you can see that unlike the other one, this bonded structure has actually managed to withstand the impact, and part of it has remained bonded and intact. Now, you can see why automotive manufacturers, for example, are beginning to utilize a combination of adhesive bonding and mechanical fastenings, because in a chassis structure, for example, this difference is the difference perhaps between broken ankles in a front-on collision and getting out of the car unscathed. And this is due entirely to this uniform stress distribution that adhesive bonding gives you over mechanical joining. And there's the final picture with the beams still intact to a degree. So, if we look at the benefits, we're looking at even stress distribution, we're looking at compensation of relative movements, we're able to bond and seal in one go, and we can deal with lots of different tolerances as well. Different materials have different surface finishes. Because we're applying adhesive as a liquid, and we can choose how well that liquid flows or stays in place, then we can join all sorts of materials with different gaps, and you can see that we can resist impact, peel and shear forces extremely well. From a cost benefit point of view, we have low inventory versus mechanical fasteners, and we have significantly better design freedom. We can choose materials to suit the application that we're designing. And if we need to, we can automate these processes as well. What we can't do, and what this next small part of the presentation goes on to talk about, is we can't just take a joint that has previously been designed for bonding, for welding, excuse me, and consider that we can take the same design and bond it. We have to consider making the joint in a manner that maximizes the benefits that the adhesives bring. And what you can see is if we load joints in slightly different ways, so shear, for example, compression and tensile, in these three manners, all of the area that we've joined is contributing to the performance that we're able to achieve, and it's all used for load transmission. Whereas, if we consider cleavage, so we're ramming a wedge in at the end of a joint in rigid parts, or we've got one flexible part joined to a non-flexible part and we're peeling the joint apart, then clearly we're concentrating the load at the ends of those joints. So the bottom two there, the cleavage and peel, are things that we want to try and avoid, and improving and increasing and maximizing the contact area, as in the cases at the top, are what we want to try and achieve, which is why butt joints with very small contact areas are bad news for adhesive bonding, because A, we have no area, and B, we can cleave those joints very easily, and therefore even the very minimal contact that we have is not all being used. See this here in a graphic that we've got with our bolted assembly. We can see uneven load distribution. Same with welding. We have peak stresses within the welds, and also we have metallurgical damage, whereas in bonding we have this nice uniform load distribution. So all that area is contributing to the bond. So what's actually happening between the surfaces when we use adhesives? Well, first of all, of course, we're always applying a liquid. It doesn't matter what adhesive technology we're talking about, we're always applying a liquid. And the reason for that is we want that liquid to make intimate contact with the surface, and we want it to take up any gaps and tolerances that exist between those two parts on a microscopic level as well. So we achieve that by applying a liquid and letting it flow into all the irregularities of the surface. And this is what gives us our bonding and sealing capability as well. We use the whole area for adhesion. There's a couple of key things that are going on within our bonded joint. The first one is our adhesion forces, which are represented here by the blue line. So this is how well the adhesive is actually sticking and bonding to the surface. And then the red lines represent the cohesive forces within the adhesive itself. So once the adhesive is set and cured, what cohesive strength do we have? So if I go back to my example of my epoxy, I've got a very stiff structure. So these red lines that are represented on this diagram form a very tightly cross-linked network. So think about something like the Bird's Nest stadium in China with all these cross struts of steel. You can understand that this gives you a very rigid material. Whereas if I take something a little different, like polyurethane here, you can see that I've got some degree of bend, but it's not hyper stretchy. It'll still carry a significant amount of load, okay? And therefore, the red lines here whilst there is some structure, there's not quite as much cross-link density, and therefore we have a slightly more flexible polymer. So it's a question of, achieving good adhesion and having the right properties of the adhesive to give us the results that we're looking for. In order to achieve one of those conditions, we need to think about how well the adhesive makes contact with the surface. And that's down to this fundamental property called wetting. So if we have a surface which is highly contaminated, for example, maybe with grease or oil, you can appreciate that when we put our adhesive liquid onto the surface, it's not going to spread out and make intimate contact because this film in between is preventing the adhesive from making good contact. So we're looking for optimum wetting. We're looking for the adhesive to spread out onto the surface. And the amount that the adhesive spreads is determined by the energy that the surface possesses and the liquid adhesive possesses. And if we were to look at a table, so what we've done here is we've selected all the non-stick materials, or most of them. Polypropylene, mostly considered to be non-stick, polyethylene, PTFE, silicone rubber, all these difficult to bond to materials. And if you look at the amount of energy they have, they're all quite low values. The adhesive value at the bottom needs to be lower than the surface energy of the material. So that's why these materials fundamentally are non-stick. If we looked at a braided aluminium, for example, we might have a value of 1,000, and therefore our adhesive would make intimate contact with the surface. And on the right-hand side, you can see the effect of doing some surface treatment. In this instance, it's plasma treatment. We get the surface energies up nice and high, and therefore we're able to bond to these materials even though they start off as non-stick materials. Before we go on to just talking briefly about the adhesive types, there's another question for you coming up here, which is which adhesive, or are you using adhesives in your manufacturing process? Okay, so we have a 3-to-1 response with regard to using adhesives. Now, for those of you that are currently using adhesives, that's very good news from our point of view, because it means that you're embracing some form of technology already. However, there may well still be other processes that you could benefit from. And for those of you that aren't using adhesives, there's an ideal opportunity for us maybe to come in and look at your processes, looking at your methodology, and seeing what benefits we might be able to bring you by using structural bonding. So thank you for that response. So the adhesive types, as I've sort of shown before, we have things that vary from semi-rigid to really flexible and highly stretchy. Now, if we look at some of these families from left to right, we're going from highly stiff to very flexible. And they tend to mirror the applications that they're being used for. So if we're bonding bicycle forks, for example, and we've got titanium and composite, then clearly they're taking a lot of load. They need to be high strength. They need to be tough and not brittle, but they need to be very high strength and not stretchy. Whereas as we move through the polyurethanes and into the acrylics and so on, across to the silicones, we get much more flexible materials, and these are used in areas where we need greater ability to withstand differential thermal expansion and contraction. We've got parts that are going to see significant temperature cycling and so on. If we are thinking about adhesive bonding and adhesive technology within our process, then evidently we need to apply it in some way. We have a whole division with regard to dispensing equipment. You might be able to see behind me there's some publicity with that regard, but it can be very simple. It can be a handheld applicator gun, or it can be much more complex automated dispensing equipment. And we can deliver large volumes of adhesive very quickly, or microdots very accurately. I want to run through just a few product highlights with you now. The first one being a product called 4090, which is a hybrid material. So what we've done is we've taken the best of different technologies and combined them. So this gives us a very fast setting system, high performance, good temperature resistance, anywhere where we're looking for high speed, fast curing. Hybrid between cyanoacrylate technology in this instance and epoxy, combining both together. The material that I showed you here, which is this semi-rigid polyurethane material, this is being used extensively in the wind turbine blade industry, which we showed you a picture of earlier. And wind turbine blades are currently the largest dynamically loaded structures in the world. So we get excellent level and balance of performance and strength against flexibility and elongation. I'll talk to you a little bit more about that product when I talk to you about one or two of the case studies that we have at the end of the presentation. The acrylics, so in this instance the 3342 material, are used extensively for magnet bonding in electric motors, for example, ferrite bonding. They have very high performance, very fast cure, and in this instance a service temperature up to 180 degrees C. Good impact resistance, very highly durable. The MS polymers used for elastic bonding and sealing, either a one-part product which is moisture curing. You can see here tensile strength 3 megapascals. That would compare to some of the other technologies, the higher strengths of maybe 25 megapascals. But we get very good resistance and very high elasticity. And if we want to go to an automatic dual cure system where we have guaranteed cure and we're not reliant on moisture, then we have a two-component product which will do that for you as well. So that would allow greater freedom of bonding of different materials that weren't necessarily porous materials, for example. And the silicone, as a last example, these are the materials that give you really high elongation to break. So you can see here over 200% elongation to break with a very high service temperature. Great if you're looking at applications with significant differential thermal expansion and contraction, large panel bonding, for example. I'd like to just show you a few case histories now. First one being the assembly of these load retaining rails inside a large lorry, container lorry. Now, the traditional way of doing this, which you can see at the top, is to drill lots and lots of holes and mechanically fix these rails in place. Now, you can appreciate the labor associated with that. You can appreciate the dirt, the dust. They have to, the speed is obviously restricted by the number of screws that need to be put through the sidewall. And then, of course, they have to seal up all the holes to keep the box dry. Compare and contrast that with the ability to bond the rails in place with a fast-setting adhesive, a structural adhesive. You save significantly on labour, you save significantly on time. you eliminate the need for the through bolts, which are very costly, and you don't have to seal the holes either. So you get a much more elegant solution, and you get a much more aesthetically pleasing finish on the outside of the vehicle. Ping, the golf club manufacturers, have been using a structural adhesive for over 20 years. In this instance, they need a material which has got significant force transmission, they need high strength, they need toughness, and they achieve that by using a two-part epoxy. Now, what the picture on the left shows is that you don't need to have, although we can do very clever dispensing systems, you don't need to make it complicated. This is a manual process in this instance. They've been doing it like this for a very long time, and Ping are associated with a very high quality of golf club, and the last thing they want is for the heads to be coming off their shafts. So we've got excellent impact resistance and fantastic durability, which allows Ping to use this process and market it and keep their name high in terms of their reliability. The third case history is a company called Eldis, who manufacture caravans. Now, originally, they were doing all the joining of the sidewalls to the roof and the sidewalls to the chassis and the floor using screws. There were over 800 screws put into the caravan in order to hold it together. And then they've got the unenviable task of trying to make that box that they've created dry. And they were having all sorts of problems with water ingress. So probably 5 years ago, we started talking to this company about the concept of eliminating completely the mechanical fasteners that they were using and considering bonding the whole thing together. Since they've done that, they've been able to issue a 10-year body shell warranty with regard to water ingress. They've completed a 27,000-mile test track testing where they tow the caravan round designed tracks which have cobbles, potholes, curbs, manhole covers, and they literally try and shake the vehicle to pieces. And on every test that they've done, this bonded van has completely and utterly remained intact. And it's a testament again to what we were talking about right at the beginning of the presentation regarding the fact that bonded assemblies have reduced stress levels compared with mechanical fastening. They always say that you should put one or two key takeaways into presentations, simply because you're not necessarily going to remember everything. So take away these things from this seminar, that structural bonding and structural adhesives contribute substantially to the integrity of these joined parts. They can and do outperform mechanical fastenings, and they give you a fantastic amount of design freedom, because you may be thinking that the only way you can continue is to try and weld parts together more rapidly, but you'd love to have one part in steel and one part in carbon fiber, or you'd like to get rid of metal parts altogether, but you don't know how to join composites. Structural adhesives are the way to do that, because they do provide you with the ability to join these materials and the ability to have, to provide you with uniform stress distribution. From an additional resources point of view, you'll find on the dashboard on the right-hand side of your screen, in the handout section, there is a white paper on structural bonding, and there are support presentations as well. You'll also find there the addresses of places to join additional seminars if they're taking place in other countries around Europe. In the meantime, you can visit the website at the top of your screen here regarding structural bonding. And if you do want to contact anybody, there's a helpline number there. There's the LOCTITE email address if you want to, or you can join me, you can contact me directly at john.dubber@henkel.com. The upcoming webinars that we have, because this, as I said, is a series of webinars, Y adhesives, instant adhesives, engineering adhesives, and all of the details associated with these you can find from that dashboard on the right-hand side. This is the opportunity for you to ask some questions if you have any, and we'll do our best to respond to any of those as they come in. I think we've got one coming through now, which is, I'll leave my glasses for this one. Do you offer training and product demonstrations to engineers at their workplace? Well, the answer to that simply is yes, we do. We try to encourage it. So if you have a group of people that you feel would benefit from this type of thing, directly in your workplace, we can arrange presentations, and obviously if we're in front of you, we can make things a lot more hands-on. We can demonstrate products to you, we can show you bonded parts, and so on. So thank you for that question. I think there's another question coming through. Glasses required. You mentioned application by equipment. Do you do this at Henkel? Yes. Well, unlike other companies, we have a dedicated Henkel dispensing equipment division. So we can offer you very simple equipment from handheld guns. We can offer you bespoke, tailor-made dispensing equipment solutions, including robotics, for automated application, whether it be bonding bike frames or whether it be bonding fans or electric motors or whatever it is you're doing, we can bespoke equipment to your needs. Okay. Do we have one more? I think possibly one final more. How can we prevent delamination of the adhesive by means of degradation on metal substrates? Well, we could do a whole presentation actually on durability and surface preparation. Obviously, we tried to touch that. There's two key points really. One is you have to ensure that you're doing the right level of surface preparation, and that might involve on metals particularly to prevent corrosion. It might mean corrosion prevention with primers. Henkel actually do have a whole division associated with surface treatment. But the other thing is to make sure that you're choosing the right adhesive in the first place with regard to the environment in service. It's a combination of both of those. We have many examples of adhesives being used in very demanding conditions for 20, 30 years plus. So we know that they're capable of doing it. It's a question of getting surface preparation right and adhesive choice correct. We use adhesives but only in limited applications due to our EMC requirements. I'm not sure who has asked that question. Can you offer products that stick and provide EMC? Is that to do with electromechanical metallic corrosion, possibly? if you email that question to me, then I can tackle that for you, no problem. Okay. I think. Can you conduct tests on our behalf if we supply parts? Again, the answer to that is we have testing facilities here in Hemel Hempstead. Like everything, it will be a question of us talking to you, working on what the project is. But yes, we can. We have testing capabilities. So thank you for that question. That sounds like something that you might want to email me directly with again, and we can look into that. The recording will be sent out also. So there's a question about the PowerPoint being available. The recording actually will be sent out to all of you that have joined online. Okay. I think that's the last question. So I would like to thank you for your participation. You have my contact details if there are any other points you want to raise, and hopefully you'll join some of the other webinars that are up and coming. Thank you.